Hello. In this fifth lecture on the PIC microcontroller 16F877, I will first of all explain the PWM mode of operation of its CCP, that is compare capture PWM section. After that, I will explain the ADC section in this microcontroller. This microcontroller has 8 channel 10-bit ADC. We will study all the details of this section of this microcontroller.
Okay, so yesterday we have discussed two modes of operation of these CCP modules. One is capture mode and then compare mode. Now the next mode of operation is PWM mode. So we are discussing the different modes of operation of CCP modules. There are two CCP modules, as you know, CCP1 and CCP2. And each of these modules can operate in the three different modes. One is capture mode, compare mode, and third one is PWM mode. So today let us discuss this PWM mode. In this mode, actually this unit generates PWM signal, pulse width modulated signal. Okay, so you can see the block diagram here. Again there is a pin associated with that CCP module. That pin should be configured as output pin, and then at that pin this unit will generate a signal which is a PWM signal. You know, pulse width modulated signal, that means for example it will be like this. Suppose you have this your microcontroller, and this is suppose CCP1 module which is being operated in PWM mode. Then it will use that corresponding pin, as you know that it is RC2 oblique CCP1 pin. Okay, so output, so it should be configured as output pin, and it will generate a waveform which is a PWM waveform. So in the PWM waveform, you know that the duty cycle is varied. That means the period is fixed. The period is fixed, is constant. Whereas the pulse width, which can be called as W or TH, this is variable. Okay, therefore the duty cycle is varied. Alright, the duty cycle is defined as TH upon T into 100%. Okay, and therefore your output at this pin may be like this. It may have small TH at one end. Okay, at the other end it may have large TH. So that is how this TH will vary. This T will remain constant. T will remain constant. Period T is constant. Whereas this TH varies. So this is your TH. Okay, so here it is almost 0% duty cycle, very close to 0% duty cycle, and here is almost 100% duty cycle. D, duty cycle. ठीक है. So that's the purpose of this PWM mode of operation. The pulse width modulated waveforms are popularly used to control the speed of DC motors. Whenever you are using a DC motor and you want to control the speed, vary the speed of a DC motor, then a typical technique is to use a PWM signal to the motor. So that means the motor is switched on here, it is switched off, again switched on, switched off, and that happens at a very fast rate. And therefore, on an average, what you see that as the duty cycle is small, the speed of rotation will be small, because the average power supplied to the load will be smaller. But when the duty cycle is large, the average power supplied to the load will be larger. Because of the inertia, the motor will not just rotate and stop and rotate and stop like that, but it will keep on rotating with a constant speed, and that speed will depend upon the average power supplied to the load, and that average power varies with the duty cycle. And that's how we can control the speed of a DC motor by using PWM signal. Okay, so that's the purpose of this. So let us see how this actual model works. Okay, now let us see how this model works in PWM mode. The logic block diagram when the model is operating in PWM mode is shown here. Just look at it. In this mode, the CCP module uses timer 2 for its operation. Timer 2 for its operation. We have seen that in capture and compare mode, timer 1 was used. It was 16-bit timer. But in PWM mode, timer 2 is used. And timer 2, as you know, is a 8-bit timer with some period register. That means it has some auto reload facility. So this is the block diagram of timer 2. Now along with this, the CCP registers that are used are shown here. Suppose we are talking about CCP1 module, then CCP R1H higher register 8-bit, and this is the lower 8-bit register. These are the count registers of your CCP module. They are also used. There is an internal RS flip-flop, you can see here. It can be set or reset, and depending upon that, the output pin will be high or low. Okay, now let us see how this works. Basically, you have to load some count in the period register. So this register will actually decide the period of the output waveform. We have seen that this period of the output waveform, PWM waveform, is expected to remain constant, and therefore this count which is loaded here, which decides the period of the output, will not be changed during the operation, but some count you have to load here that decides the output period. Then there is some count to be loaded in the CPRL register that decides the TH part, T high part of the waveform. Okay, and that may vary. If you want to change the duty cycle, you can vary the TH part. And therefore, if you consider, then in the duty cycle, suppose this is your output waveform, this is TH and this is total T, right? This T will be decided by the period register, PR2 register, and this TH will be decided by the content of CCP R1L register. Okay, so that's how this two parts of this waveform will be controlled by two separate registers. PR2 will decide the period, CPRL register will decide the high time, TH. Okay, now the operation actually occurs like this. Initially, actually what happens that, see, you have to load some count 00 initially in TMR2 register, So your timer should be started with initial count to be 0 0, right? So it's like this. Suppose it is loaded with 0 0 initially. Then you will be loading some count n in the PR2 register. That is, you can call, suppose that count is say n, count for the period t, nt. Now as this timer runs, when this count becomes equal to this, the comparator will compare that. When it finds this match, when this count becomes equal to this, the output of the comparator will set the flip-flop. Right? So the flip-flop will set, that means the output will go high. Right? Output will go high. Okay. So when the TMR2 becomes equal to PR2, so here your TMR2 becomes equal to PR2, the output goes high, right? At the same time, this TMR2 is reduced back to 0. TMR2 is loaded back with the count 0. So it is reinitialized. Okay. Okay. At the same time, the content of this register, CPRL register, is copied into CPRH register. It is shown here. Okay, you can see that the output of the comparator will do this task also. That whatever count is stored here, this count is stored for high time, n equal to nh, so high time. So that count is copied into this register, H register. Okay, so that is what happens when these two counts they match. Okay, and then your timer 2 will start running, right? The count here will go on incrementing like that. Now this count is also being controlled. It is also being compared with CPR1H by the another comparator. When this becomes equal to this, when this count becomes equal to this comparator output will reset this flip-flop. Okay, so after some time, it will reset the flip-flop. This will happen when the content of TMR2 becomes equal to CCPR1H. Okay, so that means from count 0 0, here the count was 0 0, till the count becomes equal to NH. Here the count is the count for high time, right? It is there in CCPR1 register. Till the count becomes NH, the output will remain high. So for how much time this output will remain high, that is decided by this count NH, high time. Okay, and then again your timer will continue to run. Now after some time, this timer count will become equal to PR2 register. Okay, so at this instant, what happens that we have already discussed. Okay, when this count becomes equal to NT, this will happen. This will occur as we have already seen. So it will go high, and the same thing will be done here at this instant. Same thing will occur. That means again, see when this matches, this matches with this, the TMR2 will be reloaded by 0 0. And again the timer will restart from 0 0. Okay. At the same time, what happens? One more thing that happens is that NH is copied into NH is copied into CPR1H register. So one more thing which happens here is NH, which is the content of CPRL register, is copied into CP or CCP R1H register. Okay, so that also occurs here. Okay, so all these things are repeated at this instant. Okay, so again you can understand that the whole cycle will restart. Okay, because your timer has started again reset back to 0, it will start incrementing. When that becomes equal to this NH, again your output will go low, similar as this, and your timer will continue to run. After some time it will become equal to NT, then the output will go high, and again the timer will be restarted. So that's the operation of this CCP module as PWM or in PWM mode. So effectively the output waveform is like this, where this T high is controlled by count NH, and the total time period T is controlled by the content of PR2 register. Is it clear?
हॅलो सर.
Hello.
तिथे CCP R1L आणि R1H असं दोन अलग अलग घ्यायची गरज काय?
हाँ, तो इथे काय होतं की CP तुम्ही जो काउंट तुम्हाला सी द काउंट यू वॉन्ट टू ऍडजस्ट फॉर डिसाइडिंग TH, that count should, as a programmer you should keep that count in CCP R1L register. As the cycle begins, for example here, as the cycle begins, this content is copied here in CCP R1H register, and actually that register is compared by this comparator with TMR2. CCP RL is not compared, CCP RH is compared, and therefore at the beginning of the cycle the count which is to be compared with TMR2 is taken in CCP RH, so that count remains fixed throughout this cycle. Okay, that means during this cycle it is possible that a programmer may change this content. Okay, if for example, if in the next cycle you want to change the duty cycle, you want to change TH, then by writing an instruction you can change the content of CCP RL, you can change the content of CCP RL. But that change which has occurred during this cycle will not affect this cycle operation, because the operation of this cycle, particularly the TH in this cycle, is decided by CCP RH, which is fixed, which has been copied at the beginning of this cycle from this register. तेव्हा ह्या सायकल एकदा सुरू झाल्यानंतर जर तुम्ही CCP RL मध्ये काही बदल केलात पुढच्या सायकलसाठी, then that will be taken into account only in the next cycle. The current cycle will not be disturbed. Okay, that's the reason why two registers are used. One for holding for loading the count, and other is actually used to the register which is used to compare with TMR2. Clear?
हो सर.
That's all. So I think this is the operation of this PWM mode of operation. Now here there are little details about the operation. Okay, so what you observe here is that the waveform is typically like this. So this is the time period T, and this is TH. As we have seen that this is going to be constant, but this will vary. The constant value of the period is decided by the content of PR2 register, which is 8 bit, and therefore 8 bit number have 256 different combinations. So your PR2 is 8 bit, so it may go from 00 to FFH maximum. Okay, so there are 256 steps in which you can change the period. 256 steps to change the period. Okay, so period can be adjusted in 256 different steps from minimum to maximum. That means the adjustment of the period 2 has 8-bit resolution. 8-bit resolution. That is one thing is clear from. Now second is the adjustment of the period, TH register, the T high. This T high is decided by the content of CCP, CCP1, CCP R1L register. Okay, this is also an 8-bit register. 8-bit register. And therefore again you can understand that if you want to change TH, then that will also have 8-bit resolution. You can change the high time TH in 256 different steps. But sometimes that resolution is not sufficient. Many times you need more resolution. You want to adjust TH more accurately, maybe in a smaller steps, because duty cycle will actually decide the speed of the motor. We have seen that. And if you want to change the speed of the motor with a better resolution, then these 256 steps may not be sufficient. So for that, what they have done is like this. 2 additional bits are appended to these 8 bits in CCPRL register, and those bits are from CCP-con register, and those bits are CCP1X, CCP1X, and CCP1Y. So these are the 2 bits. These are the bits from CCP-con register. So these 2 bits are appended to these 8 bits of CCPRL, so as to make the total count 10 bit. Total count 10 bit. So if you consider the CCP control register, you have to go back. Okay, so here you can see these 2 registers. CCP1, small x is 1 or 2 for CCP1 or CCP2, and this is x bit and this is y bit, right? So these 2 bits are available in CCP control register. Here it is said that these bits can be read or written, maybe. So these are typically used in PWM mode. Okay, you may put here 00, maybe 01, maybe 10 or 11. Okay, so those bits will be actually used to or they are appended to the 8-bit count in CCPRL register. Okay, so as to obtain the total count to be of 10 bits. Total count to be of 10 bits. And therefore it is possible then to vary this this particular T high time with 10-bit resolution. So this allows 10-bit resolution for TH adjustment. Okay, 10-bit resolution means you are able to change TH in 1024 steps between its minimum value to maximum value. Is it clear? Okay. Now while comparing, the question is how it will be compared, because this is your now 10 bit, so it is shown here. Okay, you can see in the diagram this is 8-bit CCPRL register along with these 2 bits, bit number 5 and bit number 4 from CCP-con register. So that forms a 10-bit count. That is 10-bit count is taken here for comparison, and the comparator will compare this 10-bit count with, it seems that it will compare it with 8-bit count, because TMR2 is an 8-bit register. But here the advantage is taken of the available pre-scalars. You know, this timer 2 has a pre-scalar. Okay, so if you consider the timer 2, so this is the timer 2 register or the functional block diagram. So even though this register is 8-bit register, there is a prescaler. So this is 8-bit, which we are currently using, and there is a prescaler, and the output of this is given out here. This is the output of timer 2, which is used by the CCP module. Now prescaler, maximum prescaler is 1 to 16. That means this frequency will be divided at the most by factor 16. That means effectively it's a 4-bit prescaler. 4-bit prescaler maximum. Okay, that means whatever is the input frequency, it will be divided by a 4-bit prescaler. 4-bit, you understand. 1 1 1 1. And then that frequency is supplied to the actual timer 2 register. Okay, because there are 16 combinations of this, with every clock cycle here, the count will increment by 1. It will increment by 1 with every clock cycle. And after 16 clock cycles, when this becomes 1 1 1 1, after that it will go back to 0 0 0 0, the prescaler count, and when it goes to 0 0 0 0, then this will increment by 1. So it means that the content of the TMR2 register will increment by 1 after 16 clock cycles. And this is achieved effectively by using a 4-bit prescaler. So effectively what you understand is that timer 2 register 8-bit, it's a TMR2 is an 8-bit register. Okay, for example 0 0 0 0 0 0 0 0, 8-bit register. Initial count is suppose this. In addition to this, there are 4 bits which are prescaler bits that can be considered to be appended to this. That's why what happens with every clock cycle, this increments first 0 0 0 1 0 0 1 0 and so on. Okay, this will remain 0 0 only. And when this goes from 1 1 1 1 to 0 0 0 0, then this will increment by actually 1. So it will now become 0 0 0 0 0 0 0 1. Okay, so it means that the count in the timer 2 register will increment by 1 after 16 clock cycles. This has become possible because of this 4-bit prescaler. That means, okay, so you can understand that even though your timer 2 seems to be an 8-bit register, along with the prescaler, effectively this total is a 8 plus 4, 12-bit count. It's a 12-bit count. Okay, for the operation of this CCP module in the PWM mode, out of these 12 bits, these 10 bits are used. 8 bits in the TMR2 register, along with 2 least significant bits which are taken from the prescaler. Out of 4 prescaler bits, 2 bits will be taken here. So now you understand that here also you can have a 10-bit count. You have a 10-bit count. So in this progression, you can imagine, you just forget about these last 2 significant bits, and you can focus on these 10 bits, and the way in which these are changing, those 10 bits will be compared by that comparator in the PWM module with the 10 bits in the CCPRL register. Is it clear? Hello? Hello, is it clear?
हो सर तुम्हाला
Okay.
हो सर
Okay, so that's how we can understand that even though PR2 is a 8-bit register, effectively it can be considered to be 10-bit register along with the prescaler. That's very important. By this you can understand how the people, the designers of these chips, they play with the electronic circuits in various different ways. In many different ways you can implement the required thing, you can get the required output. Okay, so let's go ahead. So that's how you have seen that 10-bit resolution. So the final advantage of the whole of this scheme is that now we have a 10-bit resolution for adjustment of the duty cycle. 10-bit resolution, you can adjust the duty cycle in 1024 steps. Okay, whereas period has 8-bit resolution, and that is not very important because period is to be kept fixed, it is not to be varied during a given operation. Only what you need to change is the duty cycle, that means you have to change the TH only. That's why this higher resolution is provided for variation in TH. Okay, actually what you can understand is that, for example, you can suppose the count that you are putting here, 8-bit count is this one, right? And there are 2 additional bits. So you can consider this as a integral part, and you can imagine this as fractional part. You can understand that these have 4 combinations, right? 0 0 0 1 1 0 1. So suppose, for example, your 8-bit count is suppose 0 8 8-bit count H, and these 2 bits are 0 0, then 0 1, then 1 0, then 1 1, and then it will become 0 9, right? 0 9, and this count will go to 0 0. So in this manner the count will progress, or you can change the count. Okay, so up till now it is 0 8, and now it will become 0 9. So that means you can imagine that this is an integral part, and this can be considered as a fractional part. So I can say that this is say 8.0, this is 8.25, this is 8.50, this is 8.75, and this is 9. Okay, 9.25, and so on. Okay, so you can effectively add the fractional part for the adjustment of this TH, rather than changing the TH directly from 8 to 9, 9 to 10. There are 4 sub parts which are possible, sub steps are possible. So that's how we have discussed this PWM mode of operation. Now let us see how to write program for this. As we have seen that, first of all, if you want to operate the CCP module in PWM mode, the port pin should be configured as output pin, because you are going to provide some output signal through that pin, and therefore the first step is to configure the pin RC2/CCP1 as output pin. Okay, then initialize the period register by some count. Okay, this count will decide the period of the output waveform. Okay, period register. Then initialize the duty cycle register, which is a CCP1 RL register. Maybe, see, this count has to be smaller than this, because you know the duty cycle, or this high part, is smaller than the the total period, right? So T, which is the period register, this has to be larger than this. So this is now decided by count 03 here. Anyway, so that is the duty cycle count. Then you can load proper bit pattern in the CCP1 control register. Okay, also put these 2 bits appropriately, because these bits are to be will be used along with these 8 bits to decide the duty cycle. Okay, so that has to be done in the CCP con register. So we have seen CCP control register, CCP control register. Here if you see for PWM mode of operation, only one combination is possible, and that is this one. That is PWM mode. Okay, and therefore it should be 1 0, don't care. So that is this combination for these 4 bits, and along with that you have to set these bits appropriately, maybe 0 0 0 1 1 0, whatever you want. Okay, that will be taken into account. So that is what is done here. Then you have to initialize timer 2 register, or say that in timer 2 period, and these registers are initialized. You have to initialize timer 2 registers like pre-scaler, post-scaler. Okay, and switch on the timer 2, run the timer 2. That's all. Now as soon as this is done, then this kind of waveform will be continuously generated from the pin RC2 CCP1 pin. Okay, so such PWM signal will be generated at the output. Now if you want to change the duty cycle, you can change this count anytime. Okay, so simply by changing the content of this particular register, the duty cycle of this output waveform can be varied. Okay, otherwise the duty cycle of this output waveform will remain constant. Okay, is it clear? Daya pude? Yes. Okay. Now, so we have, with this we have finished the discussion of CCP modules. 3 modes of operation as we have seen: capture mode, compare mode, and PWM mode. Okay, now the next section that we are supposed to discuss is, okay, of course you can look at this program. Okay, I think we have discussed this type of programs many times. You just compare that flowchart with this program, and you can see how the different registers are loaded appropriately. Here also you can see that your program actually will begin from this ORG00. You are selecting appropriate bank, and you are clearing the bit corresponding to corresponding to RC2, and therefore you are configuring the bit RC2 or the port pin RC2 as output pin. Then you are loading the count in the PR2 register, period register, you can see here. Then you are loading the duty cycle count in the CCPRL register, Then you are loading the bit pattern in the CCP con register, and then you are initializing the timer and starting the timer. That's all. So as per the flowchart, you can look at this program, and you can write few instructions from the program which are appropriate to this flowchart. So that gives you the initialization of the module in PWM mode. Okay, now we will go next to the remaining section of this microcontroller, and that is ADC section. This microcontroller has 10-bit ADC, as we have seen before. 10-bit ADC, and the number of input channels, 8 channel. Okay, so it has 8 channel. Bit ADC. Okay. In the last semester, we have discussed 16C71 microcontroller. That also had an ADC. Okay, for your reference. But that ADC was an 8-bit ADC, and it was 4-channel ADC. It was 4-channel 8-bit ADC. Right? Okay, compared to that, now it is a 10-bit ADC, and it has 8 channels. In this microcontroller, 16F877. Okay, so that means there is an ADC module, 10-bit ADC inside this. That ADC receives analog signal from one of the 8 channels, right? Analog input 0 to analog input 7. Okay, so there can be an internal multiplexer, you can understand. Okay, the input of this ADC can be connected either here or here or here. Okay, one of the channel can be selected for A to D conversion. The output of ADC is 10-bit digital data, and that will be stored into internal SFR. It is ADC result register, higher and lower. So there are two 8-bit registers, which is ADC result higher and ADC result lower. So total 16 bits are available. Out of that, 10 bits are used to store the result. So that's how the result is stored in these registers. That's all. Okay, so through the instruction, through the program, you can read the content of this so that you can get the output of this ADC. Okay, so once you understood this, then let us see how the ADC is managed. So there are two control registers for ADC module. ADC control 0, as you can see here. ADC control 0 register, and second is ADC control 1, ADCon 1 register. The different settings are done by these two different registers. Okay, so ADC control register has different bits like this. Again, you can see that your ADC module can be switched on or off with help of this bit. That means if you don't want to use ADC in your application, you can keep this module switched off, right? So that the power consumption is reduced. Okay. Then there are ADC clock selection bits. ADC clock selection bits, ADC S1 and ADC S2. Different options are available, and you can select one of the options. You know, ADC requires clock signal for its operation. It needs a clock signal for its operation, and that clock signal decides the speed of operation of this ADC. And therefore, different clock signals you can select FCPO by 2, by 8, by 32, or you can use an RC oscillator external. Then there is channel selection bits. There are 3 channel selection bits to select one of the 8 channels at a time. We have seen that one of the 8 channels should be connected to the ADC. Then there is a go done bit. Okay, similar bits we have also discussed while discussing the ADC in 1671 IC. So this bit has a dual purpose. Initially, when you set this bit, the conversion is started. So when this bit is set, golden bit is when it is set, the conversion is started, and after the conversion is over, at the end of conversion, this bit is automatically reset. Okay, so it's a done bar bit. Okay, so in your program you have to set this bit, and then you should keep on checking this bit again and again till it goes back to 0. Right, when the conversion is over, the bit will become 0, and that means the result will be ready in that result register. That's all. So that is about ADCON 1 register. Sorry, ADCON 0. The other register is AD control 1 register. Okay. Now here you can see these 4 bits. You can see these 4 bits. These 4 bits have 16 combinations, and they decide the function of various input pins that are used by the ADC section. If you remember that the ADC analog input channels are provided on different port pins. So different port pins have alternate functions of carrying the analog channels. So basically these are port pins, maybe from port B, port A, port C. Okay, we'll see that. You can see that in a pin signal diagram. The different port pins have alternate functions of carrying analog input signals. These 4 bits, they decide the actual functions by all these pins of the ports. See, for example, if you make this bit 0000, then all the port pins which are used for this function, they will carry the analog input signals. You can see A for analog. For example, if you put this 0011X, then you can see that all the port pins will work as digital input pins. That means no analog input signal is received. Okay, so this means that you are not using ADC currently. The all the port pins are used for digital I/O as usual. Okay, and there are variety of options available. You can see here. You can have only 1, 2, 3, 4, 5, 6 analog input channels. Remaining port pins can be used for digital I/O. Right? You can have only one input channel, for example, here, and you can use all the remaining pins for digital I/O. So depending upon the requirement, how many analog input channels you want, you can select any one of these options out of these 16 options. Okay, number 1. Number 2 thing which can be seen here is about the reference voltages, V reference plus and V reference minus. You need some reference voltage for your ADC. Reference voltage for ADC, that can be called as V reference plus and maybe V reference minus. Actually, the significance of this particular reference voltages is like this. They actually decide the analog input voltage range or dynamic input voltage range of your ADC. For example, if you make V reference 0 volts and you make V reference plus say 5 volts, then the analog input can change from 0 volts to 5 volts at the most, and then the 0 volt will be converted to all zeros, 10 bits, and 5 volts will be converted to all ones, maximum full scale output. So this is the full scale output and this is the lowest end. So full scale output will be provided for this 5 volts, and 5 volts is nothing but V reference plus. Okay, and the minimum scale output will be provided for 0 volts, which is actually V reference minus. So it is possible that you can make this particular say minus 2 volts, and you can make this particular as say plus 4 volt. Okay, so in that case what will happen? When the input voltage is minus 2 volt, then the output will be 0, 0, 0, 0, 0. And when the input voltage is plus 4 volts, then the output will be 1, 1, 1, 1 full scale output. So the dynamic range for this range, for the dynamic input range of the ADC can be decided by using appropriate values of V plus and V minus. Okay, so what you see here is there are different options available for V reference plus and V reference minus. This is V reference plus and this is V reference minus. For example, when you are going for this first option 0, 0, 0, 0, then all the channels will work as analog input channels, and V reference plus will be VDD, V reference minus will be VSS. VSS means the ground of that IC, 0 volts. For example, VSS is 0 volts and VDD is 5 volts, supply voltage of the microcontroller. So here V reference plus will be plus 5 volt and V reference minus will be 0 volts. But it is possible that if you go for the second option, you can understand that you can apply V reference to one of the port pins. Okay, so here V reference minus will be 0 volts fixed, but V reference plus is decided by the voltage that you are applying to pin number 3. So this is port A, pin number 3, which carries analog input channel 3. So this is actually RA3 oblique this. So under this option, second option, this particular port pin will not carry the analog input signal, but it will receive, it is expected that you should supply V reference plus voltage at this pin. That voltage may have any value, maybe 1 volt, 2 volt, 5 volt, positive value, and that will be used as V reference plus. It is adjustable. Okay, but in this case it was fixed, 0 volt and 5 volt fixed, because VDD, power supply voltage, is fixed. Okay, so that's how you can see that, for example, here both the V reference are adjustable, V reference plus as well as V reference minus. Right, you are supposed to provide V reference plus voltage at pin RA3, and your V reference minus voltage should be provided to RA2. So in that case, these two pins will not carry the analog input signals, but they will carry the reference voltage. So that's how we can adjust different combination, different possibilities with help of these 4 bits. Is it clear? Okay, so with this we have seen. The next thing is about this ADFM bit, this bit. This bit decides whether your result will be stored as right justified or left justified. Just now we have seen that there is a complete 16-bit space available to store the result. So there are two SFRs, address result register, AD result register higher and AD result register lower. So total 16 bits can be stored, but your actually ADC result is 10 bit only. So it can be stored in this 16-bit container in 2 different ways, either by following right justified format or left justified format. Okay, and that is decided by this bit, ADFM bit, ADFM bit. If this is equal to 1, then the result is right justified. The result that you get in this result register is right justified. That means the whole 10 bits will be stored from right side. So here these initial bits will be don't care bits, and suppose all the bits are 1, then this is higher byte, and then 1 1 1 1 1 1 1 1 lower byte. So all the 10 bits, the 10-bit result is stored in a right justified manner. Okay, whereas this is, if it is 0, then it will be stored as left justified manner. Okay, in the left justified manner, all the bits will be shifted on this side. Okay, so this is your higher byte. Lower byte will have these 2 bits of the data, and all the remaining bits are don't care bits. So this is the 10-bit data, left justified. That's all. So the manner in which the result will be stored in this register. Okay, so we have discussed the 2 control registers for ADC module, ADCON 0 and ADCON 1. Right justified, left justified, it is shown here. And so you can see the program to read the ADC module. Suppose the problem is that you want to read the analog 2 channel by status check mode, because when the ADC result is obtained and it is stored, automatically the ADC interrupt flag is set and interrupt is generated. But sometimes you may not need the interrupt, so if the interrupt is not used, then you can operate in the status check mode. So for that, in that case, you have to check the status of the ADC conversion manually. You can check the Gordon bit, and from that you can understand that the result is available or not. Okay, so here your requirement is that in your microcontroller you are going to apply the analog input signal at the analog channel 1, analog input channel 2, sorry. Okay, and you want to convert this analog signal into digital equivalent. So what are the steps needed? First, you have to configure this particular bit. For example, it is RA2 bit. So this is an alternate function on port A, pin number 2 bit. So analog input 2 is an alternate function of this. So this should be configured as input pin. So for the TRISC register, then you put appropriate bit pattern in ADCON 1 register, appropriate bit pattern in ADCON 0 register. We have seen these bit patterns accordingly, right? You select the clock frequency, you select the channel, Gordon bit should be initially 0, switch on the ADC, right? Okay, so once this is done, then disable the ADC interrupt, because here we want to operate in the status check mode. We don't want to use the interrupt, and therefore the ADC interrupt enable bit in this PIE register, we have discussed this, should be reset. Then the ADC interrupt will be disabled. Okay, and then you start the conversion. Starting the conversion means setting this go bit, and then after some delay you can keep on changing. You can keep on checking the status of the same bit. So you have set the bit. After the conversion is over, the bit will go back to 0. So as soon as it goes back to 0, the result will be available in the result registers. ADC result higher, ADC result lower, and you can save those results. That result may be in the memory. So that is how you can follow the steps to operate your ADC module. You can see the corresponding program also. So here you have putting proper bit pattern in ADCON 0 register. So there is some delay here. Every time practically when you are operating an ADC, between 2 successive steps some delay is introduced, because when you load this pattern into this register, the actually ADC module will take some time to get configured appropriately. Okay, so the next action should not occur immediately, so there can be some delay to allow this setting to occur. Okay, then this particular flag bit is reset. Okay, Now here you start the conversion. You have setting ADCON bit go bit, bit set file. Start the conversion. Again there will be some delay, and then you test the same bit, go bit. You can test the bit test file and skip if clear, and you can remain in this loop till the that bit goes back to 0. Okay, so here you are checking whether the conversion is over or not. Okay, when the conversion is over, then the result is ready in the result registers. So ADC result register higher, take it to the W, move the W to the memory location. So this is one memory location having this label. Then read this and low byte. So that is how we can store the result to the memory. Clear? So that's how we can write a simple program to manage your ADC. Is it fine? Okay. काय शंका असलं तर बोला. With this actually we have finished this unit.